So you've heard about the Open Compute project, but what exactly is it, and how do you get involved? Let's rewind. In 2009, a few engineers, hey guys, at a company, hey Facebook, realized in order to accommodate their huge influx of data, they'd have to rethink their infrastructure. So they set out to build the world's most efficient data center. And they did. But it got them thinking, if open source collaboration could create a software revolution, couldn't it do the same for hardware? So Facebook shared their knowledge with the world. And with the help of Intel, Microsoft, Rackspace, Goldman Sachs, and Andy Bechtolsheim, the Open Compute project was born. Today, OCP is a thriving global community with hundreds of member companies and thousands of engineers collaborating to break open the black box of proprietary IT infrastructure to achieve greater choice, customization, and cost savings. Our project communities are led by volunteer leaders and overseen by our incubation committee to guide initiatives in data center facility, hardware management, high-performance computing, networking, open system firmware, rack and power, security, server, storage, and telco. The result? Member organizations and solution providers collaborating to create embedded software, firmware, hardware, and facility guidelines based on OCP's tenets of efficiency, scale, openness, and impact, improving the efficiency of data flowing from the edge to the cloud worldwide. So, can open source collaboration create a hardware revolution? It already is. Join us at opencompute.org.
Please welcome Archana Haylock, OCP Community Director.
Good morning, Amsterdam. How are we today? Woohoo! Welcome to our very, very first OCP Regional Summit. The demand for a local conference was so overwhelming for a European conference that we had to listen and we responded. We are so excited to have you here, to be here, and to get started. We have a 2-day agenda packed full of plenty of opportunities for you to consume, collaborate, and contribute to OCP. So let's get started. Our first speaker today is Mark Rennick. Mark Rennick was here at the inception of OCP and has returned in 2018 to our board of directors as our chairman of the board. He is also the head of hardware engineering and is responsible for the building, scaling, and innovation of infrastructure necessary to support Facebook's mission to give people the power to build community and to bring the world closer together. Mark is passionate about open source and open standards as they increase the pace of innovation and make technology open to all. In his own words, technology continues to accelerate, and we will face new challenges to lead the drive for open infrastructure for the data center and beyond. The OCP community is being asked to help drive open architecture across this whole plane. And Mark is here to tell us all about how this is happening within OCP. Please put your hands together for Mark Rennick.
Thank you. Thank you so much. Good morning. All right. Thank you all for being here. Welcome. It's been wonderful weather the last few days. Looks like it's going to rain the next 2. So what else to do other than come to a summit and get a lot of work done? But thank you all for being here. Before I get started, I'd like to send out a few thank yous. First and foremost to the community. Thank you all for being here. Our community is what differentiates us from a lot of the other open technology forums and communities. The amount of work that gets done, the impact of that work, the contributions of our member companies is really important to success. So thank you very much to the community. Also like to thank the incubation committee, the project leads, and the project team members. I see many of you out in the audience right now. So thank you for all that you do. These teams spend a lot of extra time away from their day job, or in addition to their day job, I guess I should say. helping the foundation and the board and the community ensure that we're working on the most impactful things for our industry. So thank you to them. I'd also like to thank the exhibitors and sponsors. We've got a great selection of technology out in the lobby, so make sure you spend a couple hours out there. It's a chance to demystify OCP. You get a chance to talk to people, right, that know the benefits, the challenges, and also the best practices of open technology. So soak all that in. I'd also like to thank the OCP Foundation and our event coordinator, FN Tech. These things are always challenging to put together, so thanks to them. And then last but not least, our member companies who have been supportive from day one since we started the Open Compute project. Thank you for creating products and services for the adoption in the community. We really appreciate it. It's certainly a key success factor for us. So let me talk about setting expectations for the next few days. We've got a great event. Again, as I said, please learn from our peers. The biggest value from an event like this, right, is the peer-to-peer collaboration. We're also, IHS Markit did a survey recently that the foundation had commissioned about energy efficiency in data centers in the European market. So those results will be presented during this session. We'll also have a demo of the virtual central office. So that magic black box right over there, you'll get a demo on that later this afternoon, or actually later this morning. We also have a review and assessment of open compute data center architecture from Schneider Electric, so that you'll find that interesting. And then we also have a presentation or proposal about a solution from the edge. So stay tuned. We've also got use cases, 2 Dutch companies here, ING Bank and KPN. We've got an updated case study from Yahoo Japan, who's been a huge supporter of open compute, and also Neeram today. So how can you get involved? Tap the experience in the room. Please attend as many of the technical tracks that are of interest to you. We've got over 60 technical tracks, and that's really where the magic happens, quite frankly. The keynotes are great, but the real work happens in those technical tracks. So thanks to the sponsors and the project leads that are going to lead us through those sessions. We're always looking for contributions, specifications, white papers, products, services, et cetera. We'll provide more information on how you can contribute throughout this show. And then also a shout out to our open partners. There's 4 tables out in the exhibition hall. We've got our friends from the Linux Foundation, Open Power, Open CAPI, and OpenStack. So thank you guys for being here as well. Let me give you a quick global update on Open Compute. So at our last summit, our last global summit, which was in the US in San Jose, we had over 3,500 attendees. We had so many people, we had to turn folks away. Quite a stark difference compared to when we had the first Open Compute Summit. We called it a summit. We thought it was really cool to call it summit, and it was in a large conference room. So we've come a long way. We've had over 81 sponsors at that event, and we had representatives or attendees from over 34 countries. So truly a global initiative. Upcoming, we've got quite a few events and technical engineering workshops in Asia. Look for those upcoming on the schedule as well. Current Open Compute projects, again, this is the core of what we do. This is where the value is really created. And so you can see, back in 2009, we started with compute. 2010, we added storage, and it's pretty unbelievable to see the depth and breadth of the projects that we have here in Open Compute. And again, I think it's a testament to the work done by you in the audience and the community. We have 5 projects, believe it or not, coming out of incubation in the next 60 days. So if you have a passion or interest in those, please make sure that you raise your hand to the event planner and to the project leads, because we certainly need as much help as possible to get those off the ground. Talk a little bit about adoption of Open Compute. In last year's Global Summit, we reported that OCP products and services accounted for about $1.2 billion, and that's not including the OCP board member companies of Microsoft, Facebook, Rackspace, Intel, and Goldman Sachs. And it doesn't include the secondary market, right? And so that's quite a large number, and we believe that that'll grow to about $6 billion in the next few years. Community update. I'm really pleased to see over the last 6 months we've added several new industries. We've added a lot of academic institutions have joined the project. Many governments around the world have joined the project, and then we're getting an increasing number of fintech and financial services companies join the project as well. So a thank you to them as well. In the marketplace, where you can go and buy OCP products, we've got over 100 products that you can buy today on the marketplace, and over 100 in the pipeline. All right, so look for those goods and services over the next 6 months. And then the contribution portal, again, you'll be hearing more about how to contribute to the project over the course of the next 2 days, but we've got over 150 specifications, and that library continues to grow. It's a great source of information, and we're doing our best to make it as easily consumable to the community as possible. Last but not least, we've got a couple of events coming up from some of our open technology friends. The Open Power Summit is here, October 3rd and 4th, so right after this event. And then we have the TIP Summit, or the Telecom Infra Project Summit, in London on October 16 and 17. And if you use that code that's on the screen, OCP30, you'll get 30% off your pass to go there. All right? So thanks for letting me give you a quick update. Thanks again for being here. I want to introduce John Laban. John is our feet on the street here in Europe from an OCP perspective. He was named one of the top 10 movers and shakers in the IT industry recently. And what's really cool about John is he can cable a rack this morning, and he can teach the most complex engineering class in the afternoon. He is a wealth of knowledge, and we appreciate having him on the team. John?
Hello, so many people. I'm amazed. 2 years ago when I started, I used to ask in conferences when I was talking about OCP, how many people have heard of OCP in Europe? And I remember in one of the first ones I did, there were 200 people in the room and 4 people put their hand up. It's amazing. How many people live in Europe here? Can we just have a show of hands? Could we have the lights up to just have a grasp of this? Keep your hands up. I'm just trying. That's amazing. That is amazing. That's amazing. 2/3 of you from the European region. It's amazing. I'm really, really pleased. Very pleased. Right, let's crack on and tell you a story. Now, I'm going to tell you a story about Moore's Law on open source steroids. The impact that open source can make to innovation. These little green arrows are going viral. Does anybody know the meaning of the OCP logo, for example, sitting in the audience? Why there are all these arrows in the logo? Anybody? Any hands? Nobody really knows, do they? Well, I'm going to tell you a story about what I think they're about, okay? But it's not the actual truth. You'll have to explore the truth later. So my job, what I really do, I see myself as some kind of Greek god, like Eros. And I fire these little green arrows, okay? And when they land in people, they become passionately involved with OCP. And I'm looking at the front here, I can see a couple of passionate guys there from Luxembourg and all around me. It's so wonderful. And once they've got the arrows in them, they are amazingly passionate on what they do. And at the end of the day, it's just the people that make the difference. It's just the people. And it's about building the community. Now, what I'm going to try and do, I'm going to try and do this as a Pomodoro. And a Pomodoro is a 25-minute intense session of intense concentration. And it's used by open source software engineers. Okay? Now, it's called a Pomodoro because the guy who started promoting it used this kitchen timer. It was like a tomato, which is Pomodoro, is Italian for tomato. But what I've done, I'm jazzing it up a bit, and we've got a new Pomodoro. We've got this one. So we've got an open source Pomodoro. And what we're going to do, we're going to do 25 minutes of stuff that might be a bit radical. You'll need to concentrate. Now, in order to really kind of get into this new mindset, you really need to kind of read a broader horizon of books. And I'd strongly recommend you read these books. The Zero Marginal Cost Society and Thank You for Being Late is really showing you the way the future is going. And I had a very interesting discussion with an engineer yesterday, and we was talking about the traditional hardware companies, how they just are not changing when the world around them is changing, and how predominant open source is becoming. Now, openness starts big. We're into the 70th year of the first stored program control computer. It's called the Baby in Manchester University. And it was just open hackers, and they developed it, and then it just went on. It went over to America, it went around the world. This is the beginning of it, 70 years ago. You can go and see this computer up in Manchester. And I did a pilgrimage to it just a few months ago for its 70th anniversary. It also starts big when you start looking at all innovations. The beginning of, does anybody know why the parts of an aeroplane use French words, for example? And yet, the first flight of a heavier-than-air machine took place in America. Well, what's interesting is when the Wright brothers did this first flight, and remember, in the beginning, it was an open source sharing community, they then decided they were going to patent a certain aspect of the control system on the aeroplane. Well, what happened then, all the innovation moved to Europe. And these two brothers spent 7 years of their lives just chasing patent royalties and never really did anything more. But the innovation was happening in an open community in Europe. Now, I believe sharing and openness and collaboration, it's hardwired into our genetic. It's in our DNA. It's really there. It's part of us. And especially when you're preschool, before you go to school, school has an impact on the way you think. I'll explain. Now, there's been loads of studies done, sharing experiments. And this is a sharing experiment done with 2 children. And there's 2 pots. And under one of the pots, there's a goodie, and under the other one, there's nothing. And when the children lift the pots up, they always share. They always share the item. Always. Now, what we're going to do, towards the end of this, I'm going to get up some community members, and we're going to do an experiment just here with these boxes. And the community members are going to lift them up. There should be 4 of them down in this audience somewhere. They've got no idea what's going to happen. And we're going to see what happens. And this is a thank you for the community through these 4 people who are going to come up on the stage. But it's basically, we're going to run this sharing experiment and see what happens. Because what happens, there's the youngsters sharing, but then they send us to school. And when we get these difficult problems, they isolate us. They isolate us. I think that's fundamentally wrong. And I think what open source communities do, they change that in a fundamental way. Now, open science and open source science is about disclosure. If you look at this, Newton wrote about calculus in 1666. But in those days, there wasn't any scientific publications. He had to write a book in order to disclose it. Well, he didn't write that book until about 30 years later. Can you imagine if he had the internet at that point in time and he could just release it into the public domain, how much more rapid the use of calculus would have been? Now, that's what we have today. We have the internet. we can release stuff really fast into the public domain in a global context for everybody to use. Now, there's some very good academic studies started to come out now. This here is a link to a YouTube video of a guy doing a presentation in America about this big study. If anybody wants access to this study showing you the science behind open source and rapid innovation, contact me afterwards. Now, OCP Gear now, what it's doing from the book called Crossing the Chasm, that book I referenced at the beginning, what you see, this is the dispersion of disruptive technologies through a market. So you get the innovators at the beginning, the early adopters, and then you get this red region. And in this red region, this is where the tornado happens. This is the early majority. This is what's happening now. This technology is now going into the enterprises. And when you get into this space, there's a lot of confusion. There's often high demand, but there's no supply channel. And this is where we are now. So the early innovators, the big hyperscalers, are using this stuff, millions of these servers. You just don't see them because you never go into a hyperscale data center, many of the people in the room. But there's millions of servers going out. Now, if you just track the adoption of Linux, the Linux Foundation started in 2000. Today, it's dominant. It's absolutely dominant. And what's interesting, open source hardware is following a very similar trend. If you looked at the total production of servers, it's following a very similar trend as we move through time. Now, just to show you some of the ideas about building better mousetraps, is Roberto in this room? If he is, can he put his hand up? Right, Roberto. Now, Roberto is a chap I met about 1 year ago now in Denmark. And he did a presentation in a conference in Denmark, and he said, we need to reduce the CapEx and OpEx on data centers by 50% to have a chance for survival of enterprise data centers and not being eaten alive by hyperscalers. And he said, the only way we can do it, and I didn't know the guy, the only way we can do it is to get together and work together and create a community and open things up. Well, he's now part of the OCP community, and in March this year, he started a project, a sub-project, on modular data centers, containerized data centers. And just in this short time, they've now developed a product, they've got designs for a product, it's 66% lower CapEx than a traditional containerized solution. And there's more room for innovation that could take that to a substantially lower price. It's profound, and it happens because he communes with these talented people who self-elect themselves to come in and play with him in this community, and they're doing radical things. This is just one example. Now, it's happening elsewhere as well. If you just read this, there are no patents on Tesla cars. If you want to make one in your garage, you can do. But one thing you get from these, when you start opening things up, you get much better products very, very fast. Example here, the fastest growing manufacturer in America grew 700% each year for the last 3 years. It's an open source manufacturer. There's an initiative in Denmark for open source manufacturing across the industries of manufacturing in Denmark. The Nordics and the Scandinavians are way in front with the kind of the mental reset, how they see the future moving. This is a slide that I took from the Open Source Summit recently, and basically it says every market where Linux has entered, i.e. the open source communities enter, they eventually dominate that market, and there's a few numbers. And we're seeing it as well with the hardware side. And it's a kind of a game one story in a way. Microsoft purchased GitHub for $7 billion this year. And GitHub is the repository for all the Linux code. It's where we keep all the open source software. And they bought it for $7 billion. Microsoft contribute more lines of code into Linux than probably any other organization. They're a big, big, big consumer of OCP gear, their Olympus solutions. That's a big change. You just go back a few years. It's a profound change. There are a few other things that OCP servers do. They're just better in so many respects than your traditional servers. Have a look at this. This is European legislation that's just been voted through. And Rabbi is in this ordinance because we're going to touch on this European legislation that a lot of people might not be aware of. We're going to have a session on it. I think it's tomorrow. Have a look at this up here. At idle power, an OCP server uses 50% less energy than a traditional server. Now, part of this legislation is to address the energy inefficiency at idle power in servers. And there was a kind of a bit of a media storm in the last month where some manufacturers didn't want this legislation to go through because it was really going to hurt their product. So the compromise is they're going to delay the legislation. It should have been coming in January 2019. It's going to come in a year later, in 2020. But OCP don't need the legislation. The innovators in OCP have created solutions that are just so much better. Streets ahead. Now, if we have a look at this comparison, after the 50th year of Moore's Law, some Intel engineers did a comparison, and they took a 1971 Volkswagen, and they applied the Moore's Law to the Volkswagens. What they came out with, that the Beetle would be doing 300,000 miles per hour. It would get 2 million miles to the gallon of gas or petrol, and it would cost 4 cents. And everybody keeps talking about Moore's Law as being, everybody should be chasing Moore's Laws. It's the ultimate level of innovation. Have a look at this. Oh, by the way, they withdrew the Volkswagen last month. What this is showing you the cost of mapping a human genome, or a genome the size of a human genome. Now, in 2001, it was $100 million. Today, it's less than $1,000. Look at it in comparison to Moore's Law. Who would like to suggest why that happens? Why it's happening is because the genomics community got together in about 1997 in Bermuda, and they came up with a principle. And the principle was to release everything within 24 hours onto the internet, into the public domain. This is why Moore's Law looks like a slow walk in the park compared to what the genomics community are doing. If we had this kind of community applied to microchips, where would we have been after 50 years? Where would we be today? Take some thinking about. Do the calculations on the Beetle with that, and you'll see how fast it goes. Now, what this is the largest machine ever made by humans. And it's open, and it's called the Internet. And this is a computer-generated map of the Internet. And what it's done, it's generated these fractal pictures, but I like the picture. Now, try and imagine this. What would happen in the world without open source today? This chap came up, Stephen Johnson. For starters, the internet and the web would instantly evaporate. Every Android smartphone, every iPad, every Every Mac would go dark, a massive section of the energy infrastructure would cease to function, the global stock markets would go offline, planes would drop out of the sky. It would be an event on the scale of a world war or pandemic. And that's where we are today with open source. It's so built into everything that we do today. It's so built in. So there endeth the Pomodoro, the open source Pomodoro. Now, what I would like to do, I'd like to thank the European community, because there's so many passionate Europeans out there that are doing some really great stuff, but I can't get them all on the stage because we just don't have time. So I'm going to invite 4 people up onto this stage, and I'm going to run an experiment. But what I'm really going to do, if they could come up on the stage and come up this staircase. So we've got Robert, we've got Jean-Marie, come up on the stage, just here. We've got Menno, come up. I'll introduce you to the groups. Just come up here and stand behind those boxes. Roberto, where is he? Come on. He didn't know about this at all because, and then we've got Mark Dancy. Where's Mark Dancy? Is he in the audience or is he, no? What we're going to do then, come on. Come on. I could choose loads of people to come up, but it's a thank you to everybody. Everybody that's been involved. Yeah, these are just 4 people as a representation. And what we're going to do, we're going to give them something, but it's giving it to the community, to all these Europeans, okay, that have been involved. And we're going to do that experiment. We're going to do a sharing experiment. And what we're going to find out is how much they were indoctrinated when they went to school, okay, and how much their basic genetic kind of genome for sharing and collaboration is still in play. Now, this is the experiment. They don't know. This is all new to them. It's a big surprise. Thank you for all coming up. Now, what we're going to do, we're going to lift these boxes, and you saw with the children, lifted the boxes, and then they did something. They shared stuff, didn't they? Now, what we're going to do, we're going to get these guys to lift these boxes, to put the boxes behind them, not yet. And then what's going to happen is they're going to commune with each other, and they're going to decide how they're going to share what's there. Okay? So this is the exercise, and you have to make the decision while you're on stage, and then walk off the stage, taking with you your solution for sharing. So take the boxes off. So this is the problem they've got. Now, between them, they're going to work out what they're going to do. Let's have a look. Never done this experiment before. It could be a damp squib. So you're going to share them amongst yourselves, and then you're going to, once you've shared them, you're going to walk off with the items that you're going to take as part of the sharing exercise. So you've got to work out how you're going to share them. So what's the decision? What are you going to do?
Keep it for today, and he's going to have them for tomorrow.
Right. Now, I thought they would do that. Now, the decision, what they've done, they've come up with this. These guys, they're just innately, they just share. So what they're going to do, they're going to split them. The 2 guys in the middle are going to take a pair each, and then they're going to share them later with the others. Now, that is the ultimate sharing, and I didn't know they were going to do that, but I thought that they would. I was a bit worried that they would take 1 shoe each and walk off with it and stick it on the wall, but no. And this is what these guys do. And it's really quite amazing. I think we should give them a big hand, and a big hand to the community as well. Well done. Thanks very much.
Thank you so much. Ready? All right, what'd you guys think? Open sourcing at its best, right? Our next speaker is from Microsoft. Mark Tremblay is a distinguished engineer in the Azure hardware at Microsoft. His current role involves defining and designing the silicon and the system roadmap for artificial intelligence and reducing the cloud tax in Azure. Throughout his career, he's demonstrated a passion for translating high-level applications requirements into optimization up and down the stack, all the way down to the silicon. Deep learning has been his focus for the past few years. He's the inventor of over 200 patents. Please join me in introducing Mark Tremblay.
All right. Thank you for the intro, and good morning, Amsterdam. Thank you for making me feel just like at home. The rain in Seattle is very similar to here. Now we'll start the technical part of the day. There are quite a few slides. I'm going to take you on a journey from planetary scale data centers down to data centers, to rows, to racks, to chips. I'll share my views on AI, show you where that's going, the large AI workloads we run at Microsoft. And then I'll tie it all up together, describing the infrastructure we use, from Project Olympus, running CPUs, GPUs, FPGAs, and AI processors. And we'll see the kind of challenges we face running all of that. So let's start with the cloud, which at Microsoft is the Azure cloud. Somehow we have to build infrastructure to run something that runs all these services, right? I'm just listing here Bing and Skype and Office 365 and LinkedIn and GitHub, and it's pretty amazing the volume that we have to serve on a daily basis. So to do that, we have data centers in over 140 countries. We have 54 regions, and this is part of the flavor of my European talks. I actually list the number of fiber we have in kilometers instead of miles. I was going to put a picture of the Ryder Cup, but decided not to do so at the last minute. And then, if we dive in, here's another European flavor slide, is the data center in Dublin. Gigantic installations, and multiply this by 54 regions, and it's just an incredible installation. Then we move in at the data center level. Think about this as a stamp of anywhere between 5 and 80 megawatts, hundreds of terabits per second coming in, partition into, imagine, 100 rows. Then you take these rows and you further divide them in racks. So we have about 300 kilowatts coming in. Divide that by 20 watts, you're at about 15 kilowatts per rack. The network is now 6.4 terabits per second, down to the rack, so that about 8 times 100 gigabit coming out of the TOR. And you go down to the server, you're about 625 watts and 100 gigabits per second, so totally oversubscribed on the TOR. These numbers can be easily off by a factor of 2. Depending on geography, depending how aggressive we are in some of our data centers, but I wanted to give you an order of magnitude. And by the way, we mostly publish these specs on OCP, so you can actually get the real values there. So down to the bread and butter, 2-socket, x86 server. Unfortunately, we have to produce all kinds of variations to support different workloads, from large database systems to large storage systems. And more we're dedicating silicon and servers to computing AI. So let's jump into what AI is at Microsoft. Today, you can go in Azure and run these services, you know, in the field of vision, speech, language, knowledge, and, you know, Bing search, for example. And over the last few years, we've increased how well we do in AI. We, the industry, you know, have taken, you know, the world from a perception standpoint, a comprehension standpoint, and we're getting closer and closer, if not surpassing, what is the so-called human parity. So I'm just sharing with you here some numbers where we've gone, and it's pretty astonishing. We have a long way to go, frankly. You know, AI systems are still pretty dumb in some cases, but we're making incredible progress. And some of this comes from access to a tremendous amount of label data and, of course, incredible computing power. This did not exist in the late 80s when I was getting my PhD in computer science. We just didn't have that. And that's one of the reasons why we went through the AI winter. Now we have that, and it's really a renaissance of AI. Very exciting. Let's look at our large workloads. You know, as a computer architect, we start the workloads and try to derive how we should build systems and chips. Well, you got Bing, Office 365, Cortana, our speech platform. And they all run frameworks like TensorFlow, PyTorch, and all this is migrating to Onyx, another open network, neural network interchange that we support heavily along with Facebook and AWS. Then you look at our thousands and thousands of Azure customers. It's a little bit harder to see what they run, but you know, you can interpolate, and very similar frameworks, but usually much smaller workloads. This turns into, you know, pretty broad requirements for our AI computing. More specifically, neural networks are growing in size and complexity. I'll share with you some of these networks in the next few slides. And we often have to gang multiple neural networks and serially and train them end to end. At Microsoft, we use many recurrent neural networks. We also use convolutional neural networks, but RNNs typically dominate. From very strict latency requirements, such as Bing, where batch size is 1, that means you have 1 query at the time that we run and spit out an answer, to large training jobs that take weeks and sometimes months, where we run very large batch sizes. So to conclude, we have an infinite appetite for speed and scalability. Our data scientists have no limits in terms of what they are asking us to produce. And for all the startups out there, you know, I want to reemphasize how reliability and security are tremendously important, because these go in very robust data centers, and we just can't lower our standards there. So let's jump on a few neural networks I want to describe with you. And I thought I would introduce you to this kind of a nice animation on a classification problem. So we have, we ran an experiment, and here we have the red dots on the outside and the blue dots on the inside. So that's our training set. And we're trying to derive a neural network that will process future dots on these pictures, and our neural network should be able to classify them into the red domain or the blue domain. So we're going to design this very simple, fully connected network. See the input layers on the left coming in basically as a position, and then we randomize the weights. You see everything is connected between neurons, and at the end we get how close we are to the blue, how close we are to the red as a probability distribution. So believe it or not, we're going to take these dots that I showed you, we're going to process them through this network in the forward pass, and we're going to go in the backward pass, adjust the weights. We're going to do this 50 times. That's the training part. And we'll get something like this. So initially, the neural network doesn't really know where the red dots are. You know, so that's the red area. And look at the end. It really surrounds the blue with blue, which is what we want. Dots in the middle are kind of in between, and the red area is very isolated. So training reaches a very nice area at the end. Then the inference part would be us feeding it new dots, and it would tell us clearly if it should be in the outer region or in the inner region. And then we go from these simple neural networks to this neural network. And the odd thing about this one is, you see, the connections are not symmetrical. They're all over the place, and they look kind of bizarre. And the reason is this was generated by another neural network, not by a human. So we're already using neural networks to build neural networks. No, that's not Skynet quite yet, but you know, we're using them for useful functions. And then in 2007 at Microsoft, we beat the world record for conversational speech. You see here, we were using a CNN for acoustic modeling, another CNN, then an RNN, LSTM, and so on. So all of a sudden, you have 4 or 5 networks in the series with hundreds of millions of parameters. So you can imagine the demand on main memory here. And that's how you get those error rates down to the few percents. We have other customers who come in and say, hey, I have a problem and I need a solution. Which neural network do I pick? A phenomenal challenge. So you can go brute force and do AutoML and use a ton of computers and blindly search for the best neural network model. Or, you know, we've been working on solutions that are much more clever into finding the right parameters and the right neural networks. Still requires a lot of computers, which we don't really mind. So how do we reconcile the cloud constraints or massive scales with these AI requirements is what I'm going to talk now. So we're always looking at the chip level for something that's faster, cheaper, that can provide us quantized leap. We want to train something that takes 22 days right now and do so over lunch. So our data scientists can actually have interactive research as opposed to pressing a button and waiting 22 days. And it's got to be, of course, easily deployable in our data centers. We don't want to bring super exotic cooling technology just now. And it's got to, you know, you can try to evaluate how well these chips and systems will be at running networks that don't even exist. So I pay a lot of attention to that and look at the microarchitecture structure. So let's start with inference. Today, we use CPUs for a lot of inference. All the Cortana stuff is done in FPGAs, on CPUs. FPGAs, there's a track later on, an executive track where we spend a lot more time on this. But in Azure, in the Bing, we had strict requirements, and that's one of the reasons we use FPGAs. And we even use GPUs for image search. Online inference has strict requirements. You have a human on the other side, so we often use batch size 1. If it's just throughput and processing images on the side, we can use larger batch sizes. So on the training side, quite a bit different. You use the biggest, baddest GPUs, P40s, P100s, V100s, scale, you know, with scale-out systems. And I mentioned sometimes it takes weeks. I even ran into a job that took 2 months. It's just impossible to do research in this way. So, and large single domain reaching 100 petaflops would be great. And on the data type side, 16-bit floating point is working beautifully, and I'll show some slides on that. So it's not all about flops. In this chart, I'm showing the flops going from FP32 to FP16 basically increased by 35%, the horizontal blue line to the orange one. That's fine, but if you lose a little bit of accuracy, that may not translate directly into commensurate training time reduction. So that's those curves, and again, blue and orange. In this case, we saved some time, and this was run on NVIDIA card. I happened to have a meeting with the leader of that division on Friday, and that has improved tremendously. So we're still in an era that things are moving so fast, and now you kind of see a 2x improvement from going from FP32 to FP16 and sometimes more. So our choices literally is to pick for training and inference between all these technologies. Let's go first in CPUs. Well, we use millions of them in our data centers, and sometimes they're free. Hard to beat free, because we don't use them 24/7, 100% of the time, right? So we use them for inference. Our partners and our customers use them also. And the ISA is evolving nicely and rapidly from Intel, AMD, and the ARM ecosystem. I have a slide here that Intel shared with me. You can always tell it's an Intel slide from the fine print at the bottom. Lots of that. But I wanted to show the improvements going from 1x to 2.8x in a couple of years. That was just pure software. Going to 8-bit data types, 5.4x, going to AVX512 plus new VNNI instructions, 11x. We're just talking about Moore's Law in the previous talk. Wow, this is a lot faster than Moore's Law. This is not like spec-int evolving at 10% per year. So we're going to see some tremendous improvements in the last few years. So don't dismiss CPUs because they're CPUs. For us, that's kind of the bar. Anything, you come in with a new accelerator, it better be 10x better price performance, right? And CPUs establish a pretty nice bar, given that there's security and there's virtualization and plethora of software that's available. Internally, we optimize the whole software stack. Here, we were at 107 milliseconds on this app, which was not shippable. And we just put an army of Microsoft software geniuses that shrank that by a factor of 20, just through software. All right, let's jump to GPUs. King of the Hill right now is large V100, 815 square millimeters, 300 watts, handles all kinds of data types, tensor cores, and proprietary interconnect. Very good machine. It's pricey and doesn't do so well on some of the neural networks, but currently the king of the hill. You stack 16 of them in the system. I'm not showing the heat sinks in this picture, fairly sizable, and you get this GGX2, $400,000 machine that currently is very hard to beat. At the inference level, NVIDIA just disclosed the T4. The picture is from them, the bullets, and from me. Actually, I think it's a quite nice machine running 1-bit, 4-bit, 8-bit components, 16-bit components. And they added virtualization. They added better tools to jack up the throughput for low batch sizes. So it's an interesting processor for inference either in the data center or on the edge. Let's jump to AI processors. Wow, this is the wild, wild west. There's billions of dollars being invested here in Europe, in China, and in the United States. I've personally talked to 40 companies designing AI processors. They all address either inference or training. All of them rely on an intermediate graph representation and all running their own software stack. It's going to be wild. Not all of them will be successful, but the technology is pretty amazing, from optical computing, analog computing, and gigantic CMOS chips. Two categories are emerging: companies relying on fast external memory, and others try to leverage as much memory that's available on chip. Let me spend 2 slides on bandwidth, or 1 slide on bandwidth. So if you take the current state of the art, you have a 100 teraflop machine for basically 1 terabytes per second through 4 HBM2 stacks. So that's 1 byte per second for 100 flops, or 1 byte for 100 flop. In the old HPC days, the folks were asking us for 32 bytes per flop. So it's the other way around, right? The ratio is basically 3200x. We don't need that, so we're shrinking data types, we're exploiting locality, internal bypasses, we prune networks. Well, we're a long way from a factor of 3200. We need another factor of 25 to 50. New SerDes, more HBM2 stacks, HBM3 stacks coming out will give us an integer factor, but not a factor of 50. So the other approach is to try to locate most of the neural network, if not the entire neural network, on chip. And in today's technology, you can fit reasonable sized neural networks. I'm showing a bunch here that would fit in an on-chip memory that's totally doable in 16 nanometer. and easily doable in 7 nanometer. So either technology requires a lot of power and systems to handle these high power accelerators. So I'm going to share a couple with you here, and also there's an executive track later on discussing this, but here are 2 systems that we worked on with ZT. The first one is a couple of Intel sockets and 12 P4s. I was just talking, the T4s has fallen onto that. So, you know, pretty nice box, dense box that accommodates all of that. The next one has a couple of AMD CPUs coupled with AMD GPUs. These are ZT systems that are at our booth as well. So, you know, you start ganging these, plus the other system we described in the past where we can pile on, you know, 8 cards at 300 watts a card. There's a, you know, 3,000–4,000 watts. You put 8 of these in a system, all of a sudden you have 30 kilowatt racks. How do we deal with this? Well, fortunately, with Project Olympus, built in enough, you know, headroom to be able to provide enough powers and potentially cool these hotter racks. So AI in general, you know, as different needs. Right now we're renting VMs that are not really related to each other, and if they are, you can connect them somewhat loosely through the Tor. With AI and data parallelism, these processes need to be much closer in bandwidth and in latency. So that forces us to really design systems that are denser than what we were doing for general purpose computing. And therefore, the impact on, you know, mechanical and thermals and for data center, for on-prem, for the cloud, and even on the heavy edge. Let me conclude. So certainly, hyperclouds provide the massive scaling, right? If we translate this into advances that I see out there for AI in hardware and software, I think we've got an easy factor of 100 in front of us, and I can kind of see the 1000x. Much better than Moore's Law. And the next few years are going to be quite phenomenal in terms of advances. I shared with you challenges we have with power distribution and cooling. We've got to find more exotic solutions in that space and discuss the impact on rack systems and data centers. To finish it all up, you know, AI can do a lot of good. We have to be careful how we steer it, but the combination of incredible hardware, software stacks, incredible technologies, plus all the scientists working on this just point to a very, very bright future. Thank you very much.
Hi, everyone. That was amazing. We have our next speaker coming up. Just give us a few seconds to get caught up, and we'll get started here. Our next speaker is from Facebook. Hans-Jürgen Schmidtke is the Director of Engineering in Facebook's Infrastructure Foundation team, based in California. They engineer Facebook's network infrastructure. In past roles, he was at Juniper Networks, where he actually was responsible for the architecture of SDN, data centers, access, edge solutions, and wireless LAN. He was also the head of fixed network operator business in North America for Nokia Siemens Network. That is now part of Nokia. Dr. Schmidtke has done so much in the field of telecom and edge. He's the chair of the Open Optical Packet Transport Working Group within TIP as well. Busy guy. Today, he will be discussing the challenges that Facebook faced in designing and operating their flexible and efficient infrastructure, an infrastructure that has growing component limitations and extremely demanding workloads. Please welcome Hans-Jürgen.
Thank you very much. Thank you. Good morning, everybody, and welcome to OCP. Thank you for inviting me. We have a lot to discuss in 25 minutes, so if there are any questions, and there will be many, many questions remaining, just come to me. I will be at the booth and approach the staff, us, and we can discuss. So I guess the title is Distributed Compute. We talk about compute, but it will actually be mostly about the challenges we have when we build data centers. And those are changing all the time. You've probably seen a lot of KPIs, key figures, how large hyperscale companies are. And I didn't want to bore you too much with those, just a few here. And that gives a little bit of a perspective. If you have to operate an hyperscale data center that has to deal with more than 100 million hours videos watched on Facebook daily. Just imagine how many lifetimes this is just on a day basis. Or you have to deal with uploads of 95+ million photos every day. So you have to start learning, not just megabytes, tera, exa, zettabytes. You have to start learning what those exponentials mean. But also, you have to have fairly low latency demands in terms of voice calls every day. You can see there's a lot of applications that are hitting our data centers and our network. So in summary, how do you deal with that? You build clearly data centers. So these are 15 data centers we have announced. These are data center sites, actually. When you look at every individual picture, there are several buildings, up to several buildings. Sometimes we start with 2, and then we grow this out. So this is quite significantly increased. A couple of years ago, I think I just showed 4, and now we have 15. The most recent was announced in Singapore. And they are distributed across the world. It's nearly by definition distributed compute. You have these data centers all over the world. And in the background, you see this map that is essentially the 2G, 3G, and 4G connections that we see on Facebook. And that kind of gives you a little bit of feeling where our community is. What you don't see is those people who are not connected to the internet. And therefore, you see a lot of dark spots in the world, and it's always good to remind us. What you also don't see is our terrestrial and submarine networks, as well as the caches that are very, very important to deliver the experience for our community. So what's really happening in the last years is shown here in this slide. We started essentially just by providing some level of texting. What is now in today's terms more or less, a byte game. It's not much. And if people start putting photos on the websites and videos, you literally make the move from megabytes to many more megabytes to immersive experiences. So what we see is essentially over the last years, more and more quality of posting, higher demands in terms of storage. We see an increase of the community, but we also see an increase of the frequency of the posting. So mathematically spoken, this is actually called a super exponential increase in demand that we have experienced. And so it's pretty exciting, actually, to see that happening. But essentially, this is only what you've seen right now, the machine-to-person traffic. That's the lower bar on this slide. So it's increasing exponentially, as I mentioned, but it's obviously not the major traffic driver in our data centers. That's the machine-to-machine traffic. So this is essentially what I just showed, the Italian movie. But what you don't see is necessarily what's happening behind the scenes inside the data centers, and we will talk a little bit about that. So this looks like a sea change, a more or less continuous sea change over time. But when you actually double-click into the traffic and actually look at the traffic patterns of a server over time. And please do not read too much out of this graph. This is a classical graph that should confuse you. that when you have a look at the flash capacity utilization and the I/O of it and the CPU, you hardly see a correlation over several months. That's happening on a server level. And that's really important when you run a data center, because that really determines your utilization degree, how much investment you have to make into those data centers. So it's not a sea change, a slow sea change, an exponential increase over a year or two. It also really matters what applications run on a different server, because that really determines, in the end of the day, also your degree of utilization and the capital expenses and operational expenses you're facing. So it's really hard to predict at times. And at times, utilization, in this case of flash, would be very, very low. And it really requires, here when you look at that, a proper scaling of compute, network resources, and storage resources fairly independently. Because now you can actually scale it as you need it and not just be defined on a certain server. I think this is one of the key challenges we face when we build data centers, is to make sure that we optimize the resources. And so what resources need to be optimized? And I just wanted to just put that out, because sometimes we look at that from a sheer bit optimization angle, but really starts with also the people, right? What is the staff available? What are the engineers, literally from architecting, from the initial idea to actually the landing part is actually a very, very important aspect. The scale, what is extremely important. I mean, it sounds funny, but it's really difficult to get the equipment at that scale in time as we need it. We have, of course, we are constrained by power, thermal airflow, space, and in fundamental economics, and the timing is extremely important. So when you look at all these degrees of optimization, and then you need to balance the operational aspects of, do you view operational simplification more important than some of the feature requirements, or do you want to scale it out, let's say more fiber, or do you want to scale it up in speed? Software, hardware, disaggregation is a big factor, and what is available in terms of technology. So there's many, many considerations that go into an optimization of a data center, and I believe at times when I look at just a mathematical model, it's easily forgotten how many constraints there are, and also moving boundaries. And essential for all of this is we as a single company cannot solve for it all. That's why we believe in the open community. Here, OCP and also TIP was mentioned, is that we actually build an ecosystem together and work on those very, very hard challenges that are actually relevant for many industries together. So OCP since 2011, TIP fairly new, 2016, more focused on the connectivity to the people and driving the internet to the people, but also driving new tech into the telco industry. But fundamental to all of this is building the building blocks. And here you see in the Bryce Canyon and Lightning, these are our JBOD and JBOFs, just a bunch of disks and flashes that we submitted to OCP. When you look then at the memory aspects, you see here 2 processor systems, each with 256 gigabyte RAM and 25 gigabit NICs. Is another building block. It's like a building block for building the entire data center, and the compute, of course, with Linux servers. And they just happen to have a high amount of CPU compared to RAM, but there's still a relation between CPU and RAM. And all of this together form, in the end of the day, data center with and listening to this great talk before with ML and AI accelerators that we work very hard on, build essentially the optimization pieces. This is the simplest architecture of a data center I've ever presented, but essentially shows you these are the fundamental building blocks we start with when we start the optimization, as we then wrap a network around it and build the connectivity. So this sounds great. you have a complicated problem. We built an ecosystem. We have the building blocks. We built everything from and build a data center. So what's the challenge? There are many challenges, but when I double-click now into those components, and I will do that now, we see a lot of challenges. So let's start with the CPU performance. The CPU performance over time, what we see is increasing, but not as much as Moore's law would have predicted. So, and that is the yellow part. What you see happening is the blue part. And so essentially CPU performance is not as quickly increasing as the demand would actually require it. There's a lot more detail around HDDs. We see when you look at this dashed line, that is what we would have expected. The increase is the low line, the green line, the percentage year-over-year increase. We don't see much terabyte increase anymore over time in HDDs. At the same time, we have a challenge, and you can see that on the right side over time, that the I/O of the HDD normalized per gigabyte is actually reducing. So that actually imposes a lot of challenges for many of the applications we are running. So different reasons, not necessarily driven, of course, by Moore's law in this case, but still a big challenge on a component level. Now let's talk about the challenges on the switch chip level. Here's a table here with the throughput of the switch chips. Today, in the year 2018, 6.4T is probably the standard in switch chips. SerDes is 25 gig speed. Ideal optical speed would be 200 gig. And the implemented at scale, what we see right now is only 100 gig. And you can see and sense already the challenge. And when we predict the next years, you can see that actually the switch chips are still improving by a factor of 2 every 2 years. What is not bad? There's many things you can do. You can increase the die size. You can optimize. So that's actually a good news story. But when you look at the SerDes, well, they are actually not increasing as fast. And then the ideal optical speed in the next years is absolutely lagging behind. And so I would say in terms of the actual optics and actual at-mass deployments, the optics is running 1 to 2 generations behind. And what you can also see is that the power, mostly driven by the switch chips, are reaching limits that are unsustainable for deployments in data centers. So essentially, there's many challenges around optics, power, scale of SerDes, and the general I/O scale of the chips. And so there's a real dilemma. We believe we need to tackle this as a community. So in summary, there is a challenge in terms of demand versus supply. So we have the demand is increasing. Italian movies, you might remember the slide. And also the post-processing we're doing drives a lot of bandwidth. At the same time, the fundamental technology supplies are lacking behind. Yes. In AI and ML, we also we announced it just a week ago at an at-scale conference. We tried to catch up also by building components that allows us to be more specific with the workload. But in general, we see challenges that the technology breaks. And it manifests itself typically in a power problem. And with this comes a cooling problem, an airflow problem. And so what can we do about it? It's really a problem statement, but what can we do about it? We can do a lot about it. And I give you here today just a few options, and I will run through 3 examples what we can do about it. First of all, you always can do topology and protocol optimization, where you put in place the resources. You can always balance high versus wide. We can, as an example, for high versus wide is as SerDes speeds and optical speeds do not increase fast enough, there might be the option to just deploy more optics and more fiber. So you become wider. Or start building actually on the component level. ASICs are called for reason. ASICs, application-specific ICs. So we have to look at that. Plus, we have to look at the optical components aspects to it. So let me give you 3 examples that basically show you that there are options to deal with those challenges, but those options require a much stronger community engagement. So first of all, to start with, when you have a single server and you have defined resources of CPU and memory and storage, it's obviously not optimal. I showed you this example over a year or so, how the demands on a single server are actually changing. So it makes a lot more sense to actually pool memory and storage or certain elements somewhere else and really have that grow independently. That's a fundamental principle of disaggregation. And we do that because we want to disaggregate. We want to solve the problems or the challenges or the resources independently of each other, and so that's why you disaggregate. But in this case, when you do that for Flash, you put a lot more burden on the network. So it becomes a balancing and optimization between network resources and Flash resources in this case. And that's actually being simulated and optimized, and we actually see this as a viable alternative. But that also means we need to start looking at innovating in the optical space, in the networking space. And that's where leads me to the next chapter. We, as I mentioned before, have a challenge, a power challenge, in the scaling challenge in the networking space. And we believe that the next generation optoelectronic revolution will be in the integration of optics with electronics, with switches. And we call that, in this implementation, co-packaged optics. So essentially, power is a shared resource between network and servers. And when you use more power in network, you take it away somewhere else from servers. In general, servers deemed for compute and storage are very useful, of course, for the community. In this case, it's becoming a balancing act. So the more power I can save on the end of the network, the more I can give back to the server world. And so where's power lost? And this is a breakout of the power we see in networking. And you can see the largest part, the 36%, the yellow below, is essentially the switch function. Clearly, the switch function I cannot really optimize. I need to switch. But I can optimize a couple of other elements, and I like to point out the elements of the I/O. And this is the I/O of the optical and the switch. It's essentially driving the lanes. I would even say these are maybe the most expensive heaters on this planet. These are the copper lanes that we have to drive on the board. And we see 20% just there. That doesn't sound too much, but when you look and predict what's happening in the next years, and then look at some of the designs in the next years, we actually think that this figure of power optimization is actually more closer to 50%. 50%. And that's where you start thinking, should I use pluggable optics or should I use a more integrated approach? And that is a game changer. So the design goals are essentially reducing the lanes. So when you want to reduce the I/O drivers in chips, you want to reduce the lanes between the optics and the switch chip. And in this graph, you see the depiction of, on the left side, of the switch chips, and on the right side of the pluggable optics. And the white is essentially the symbol for the copper lanes. And the idea is to reduce this white. You can see that from onboard optics down to co-packaged optics further. So what we do essentially is we bring the optics closer to the switch chip as a first step in terms of onboard optics, a first reduction, and then ultimately bring it into the package so that you have the smaller distances so that you don't have to drive the copper lane as far. So the bandwidth reach product is being significantly reduced in terms of the copper medium, and that gives us the belief, this is really what we believe in, is that can reduce the power significantly. So those technologies that you see here right now can be not just used for switching, it could be used for routing, it could be used for optical NICs, it could be used for low latency buses in the AI clusters of the future. So this is a very general concept. And we believe that it will be very relevant. And this is a depiction of what we see is possible in the first generation. We believe that in a switch chip we can actually integrate 128 of those pluggable optics. By that, not just reducing power, but also allowing a better manufacturing model that will carry us into the future. So I had to count it through. It's actually 128 optics. So how it's actually being done, there's a whole theory around it, is, and people work on photonic integration for many, many years, is actually you see the substrate and you have a photonic die on it and a switch die, and you common package it together. And there's many embodiments of those designs that we see evolving. So I mentioned before, we put more burden on the network. We balance resources, compute, network, and storage. And we need to start innovating on the component level. But there's, of course, also, in general terms, the opportunity to do even wider topology optimization in the network and in the wider network. So what we call scale-out of the fabric aggregation. We actually announced that at OCP beginning of this year, and let me explain you what that is. Essentially, when you look at the traffic flow in the network from the community to the Facebook network appliance and caches, through the points of presence, the wide area network, and the backbone into our regions and data centers, you can see that there's a lot of hierarchies of networks. And there's one particular hierarchy that we call fabric aggregator, that's essentially the connection of the backbone towards the data center buildings. And this hierarchy is called fabric aggregator, and it connects the data center building to the network and the data center buildings to the data center buildings. And so this is typically laid out with 100 terabits and several hundred terabits in the next outer years. And it's usually one of the higher utilized parts of the network. And so we looked at how can we solve for that. And we built what we called the fabric aggregator. And this fabric aggregator is actually the embodiment of disaggregation and integration. And it consists of a very simple single element, the Wedge 100S, 3.2 terabit per second, that we stuck up and built with the software a whole 100 terabit per second switch. Essentially, this is actually not just one single static configuration that you need to imagine here. We started building a backplane that is essentially allows us to connect many of those switch elements. And we didn't just do it once. We tried to figure out what can we do to which technologies make sense. So we have engineers who are very passionate about copper backplanes, and we have engineers who are very passionate about optical backplanes. So we looked at why wouldn't we build all of those? So we did pigtail, active optical cable, CWDM4, PSM4, and DAC cable. And assemblies and that connect those Wedge 100s. And we worked with our ops folks and tried to figure out what is the best solution. For us, the best solution was CWM4, but essentially, if the solution for you is something else, it might be very well working with a DAC cable or for smaller sizes. And that carries me to close to the end of my speech. because there's just few elements of tech we're building for some of our applications that I believe are actually very, very relevant for many other applications. So just the last one was we built actually an optical backplane or a copper backplane that allows you to scale from a few terabits per second to maybe 100 terabits per second as you wish, based on smaller elements. So you don't need to build and buy a huge fabric that is essentially one size. You actually can build something even pay as you grow, right? Based on those techs we have done. And you doesn't need to be in the fabric aggregator space. It could be even in the wide area network somewhere or in other places in your data center. So essentially we build backplanes that allow you to connect and aggregate larger spaces. In addition, when you look at what we look at right now, what we want to solve for is we want to solve for the I/O problem of chips. That's such a wide space. It's not just an I/O space in a specific data center of a specific hyperscale company. It's actually a much wider problem. And so we're very happy to listen to the community and understand the wider problems, because we actually believe this type of tech will penetrate in nearly all applications in the next years. So it essentially touches telcos, any data center size, because you don't need 100 terabits. You can do the same thing as I just described with 10 terabits. And of course, hyperscalers. So in summary, this is, I think, what is OCP for. It gives also the forum to have those discussions. We see in general that our demand cannot be met by the supply. We need to start innovating. And innovation will happen in many, many facets, in many, many areas. One of those, of course, is topology optimization. You start optimizing where the resources would fit in. But we also need to look deeper and deeper into component-level development. And I gave just an example on co-packaged optics, but there's many, many more examples around ASIC and ASIC designs. And then, of course, scale-out of networks. Scale-up versus scale-out. I gave you an example for scale-out, and scale-out in this case would have been the fabric aggregator, where you can build something much larger based on fairly small devices. And all of this has tremendous industry applications. Essentially, any end-to-end cloud architecture can make use of the tech, I believe, that we just mentioned. Thank you for your attention.
So folks, we are very, very excited. The fabric aggregator that Hans-Jürgen just referred to is in the Facebook booth out there, so you can go check it out. The GPU appliances by ZT Systems that Mark Tremblay talked about for Microsoft are also out there. You can go check it out. As Mark Rennick talked about in his speech earlier, we have over 100 products in our marketplace and 100 more in the pipeline. So you can go out there and talk to the folks that are in the booths, see those 100 products that are available today, and possibly get a glimpse of those other 100 that are in our pipeline. So very excited to have our exhibitors out there. Please do go visit the booth. Next up, I'd like to introduce somebody very special. Bill Carter is OCP's Chief Technology Officer, our CTO. Now, CTO means different things according to Wikipedia. And in Bill's case, I could look at all of the definitions, and pretty much all of them apply to him. Concurrent training and operations, that's Bill. Configured to order, that's Bill. So we're pretty excited about everything that Bill's doing, and he's a respected subject matter expert. He's had 35 years of experience with Intel, and he brings that over to us at OCP. Please join me in welcoming Bill Carter, our Mr. Check This Out, CTO of OCP.
Thank you. Thank you. Hey, it's great to be in Amsterdam. We started on this journey 2 years ago, and like John Laban pointed out, there was just a few people that we would talk to, and it's so enjoyable to see a full crowd here today. I'm going to spend the next 8 or 10 minutes and talk about what's in store for the rest of the day today as well as tomorrow. We start off in the afternoon with 9 different executive tracks. Just quickly cover some of those. By the way, all of this is available on your iPhone app, so you can find that information on the back of your badge. One of the executive tracks is from Inspire. They have several new open source products that they're planning to introduce. They'll cover those in their session. Samsung's going to give us a look ahead on what's going on the non-volatile memory roadmap, and we'll get a flavor on what's the technologies to come there. Facebook is actually going to present and talk about the journey of open sourcing, and that should be a fun topic to sit and listen to their journey and the individuals that are involved in it. And then we're also going to have a discussion from IHS Markit. They do some market surveys for us and help guide us as an organization. They're hosting a panel in one of their executive tracks and talking about that journey with some panelists. So again, you want to, as you start on that journey, maybe you can hear from the folks at Facebook and the IHS Markit panelists and listen to their journey. Microsoft is going to talk about the benefits of specialization using common FPGA technology. Mark mentioned that in his talk earlier, and so he'll go into more detail on that journey and the use of their hardware. NZT Systems is a supplier of the Olympus system. They're going to talk about building cloud hardware solutions using the Olympus platform. IT Renew and WeWin will talk about new products that they have in the pipeline, and they're very supportive of this open sourcing movement and expect to see some interesting information, product information from there. And Hewlett-Packard is going to talk about autonomous driving. I think I'm going to attend that one in hopes that we can figure out how to quickly get autonomous driving involved in my wife's vehicle so she stops running into the garage door. We also have brought some adoption stories to this summit. We have 4 companies that are going to speak in a session this afternoon. ING Bank out of Poland is talking about how open compute and OCP hardware has helped them with their TCO challenges and reducing TCO costs. Booking.com is also on this open source journey, and they're going to talk about some of the challenges that they have come across and how they've solved those and help explore that open source journey and the use of OCP hardware. KPN Telecom is again going to talk about their use of open rack technology. And then we have a group from Nurum who's teamed up with Solaris and IT Renew, and they're a cloud service provider out of France, and they'll talk about their journey as well. So it should be a good session this afternoon. We also have, for those people that are new to open computing, they want to learn a little more about the organization, we have a special track where we're going to talk about what it's like to get involved in OCP, the various groups, and talk about how do you get involved personally. Archana Haylock's going to teach that. We call it our OCP Primer. We also have a pretty robust marketplace where our solution providers and people that build open hardware can advertise and share that information, all their design specs, design files, and product information on that marketplace. And so as a service that we provide to solution providers, and we have several in the audience today, we've added some security to that website. We've added some tools to allow them to service their customers better, and Rajiv's going to cover that. As Mark mentioned and Hans-Jürgen mentioned, we have a huge challenge ahead of us to solve the cooling challenges, cooling from GPUs, FPGAs, as well as the challenges in optics and the heat dissipation we expect from 400 gig optics. And so at our last summit in March, our global summit, we announced the creation of the Advanced Cooling Solutions Group. That group has had an initial kickoff this summer in the Bay Area, and we plan to have a session tomorrow. But they're very excited to get together. They have a long list of things that they want to work on. And so they're actually going to meet this afternoon at 1 o'clock and start that effort. So they're going to spend the afternoon together on day one. And we actually have a special guest, Octave Clave, CEO of OHV, is going to kick off that session. Turns out that OVH has actually installed over 300,000 servers using liquid-cooled technology. So he's a guest speaker in that session at 1 o'clock today. On day two, workshops. We try to have a workshop for all of our projects. So we'll have a server and storage project, network, rack, and power. We do have a security project, and because we just didn't have enough time for all the projects on day two, we're actually pulling the security project in, and so there's a presentation on today on the security, and specifically a presentation from Microsoft and the Cerebus security solution they're open sourcing. We have work going on in our management group. Again, the advanced cooling group that's meeting today will also have a session tomorrow afternoon, talk about various things. So we've kind of combined that with HPC. We have a pretty active telco work group, and there's actually a lot of products that are going to be discussed at the spec level, as well as some products that are kind of on the back end and going to market. So EdgeCore has a cell site gateway that a specification that they're contributing. There's an aggregation router that's being contributed. Deutsche Telekom's been working on with some of the other European carriers and has come up with a GPON specification that meets their needs, and ideally that's socialized in these work groups and aligned with the supply base to build these open source products. So that'll be discussed. I think AT&T is even talking about their cell site gateway router specification as well. So again, a lot of things going on. There was mention earlier of an Open Edge subgroup that's being formed and being incubated. Mark mentioned that earlier. That'll again be discussed in the telco work group. And we also have a data center facilities group. I'll talk more about that in a second, and our open system firmware project. So pretty full day, about 60 different presentations tomorrow throughout the day. The server and storage groups are actually being combined into one. I think there was mention that Yahoo Japan had given a presentation at a summit last year. They're back again this year, and they're going to talk about their journey. About 25% of their facility has been switched over to OpenRack, and they're going to kind of give us an update. That's going to take place in that server and storage workshop. We also that team released a Mezzanine 3.0 specification, also referred to as a NIC 3.0 specification. It authored by a dozen companies. They spent the last year working on it. It basically takes PCI Gen 4 and electricals and puts a new package that's pluggable from the front of the system. So there's two different form factors. They'll go into disclosure on that spec that's been released. And then we have a variety of GPU boxes and storage boxes that have either come out or are coming out. And I say coming out, being contributed and open sourced. And so those will be covered in that joint session as well. And I think if you visit in the exhibition hall, you'll have a chance to see some of those products. Again, things that are either in the pipeline or things that were recently introduced. So it should be a good session. I mentioned data center facilities. We actually created a new program for companies that provide co-location services. And so the logo on the left, Colo Solution Provider, helps identify those companies that are part of this provider network. Now, as a provider, you operate facilities. We think that there are certain requirements that should be implemented in those facilities to really gain the efficiencies and implement the best practices, some of those efficiencies that are defined in our server and storage groups. And so that group has actually defined a checklist of best practices to drive that efficiency. And so facilities that meet that best practices guideline will actually get to receive this OCP Ready logo. And so that's being rolled out, and they'll talk in more depth about that in the data center group. And finally, on day 2, we also have a European focus track. Again, just more information available. So Mark Rennick mentioned this morning that we had had IHS Markit conduct a survey on our behalf and look at what's important in Europe, and particularly around energy efficiency. And so those survey results are going to be shared by Liz Cruz and her crew in one of those sessions. We'll also hear from the London Internet Exchange. They've adopted open switchgear hardware, and they'll talk about that experiences and the savings. Also mentioned by one of our speakers, I think John Laban mentioned the challenges that EU policies are having and the effects that those policies may have on the data centers, particularly trying to drive efficiencies. We're very fortunate that most of the products that have been contributed in open source to OCP really meet those already today. So we've been able to put together a panel of folks that are involved in this EU policy setting, and they're going to describe some of those upcoming policies and be able to have a Q&A. So that's again, one of those sessions. We call it the European Focus Track. That's on day 2. And then the final one is the Research Institute of Sweden. We've been working with that organization this last year. They've installed some OpenRack V1 solutions, and they've recently installed or have received some latest version 2 systems. They're doing energy studies and comparing that. And again, that information will be today. I think tomorrow they're going to talk about what they're doing. But the goal is that we help the European community make good choices and try to solve some of the energy issues that we face. In the Global Summit in March, we announced partnerships, collaboration agreements that we have with a lot of the other open source organizations. And as Mark pointed out, we work hand in hand with the TIP organization. We also work hand in hand with Open Power. In fact, when we decided to have our summit here today, we coordinated with the Open Power folks, and their summit follows on Wednesday and Thursday this week. So feel free to encourage you to stick around and attend their summit. Back in March, we introduced some collaboration work we were doing at the Linux Foundation, and specifically the NFV group within Linux. And that collaboration is really based on, we want to offer open source hardware, and we want that hardware to be ideally optimized to run with, with their open source software. And so that work actually started probably a year ago, and we've been working with our solution providers, Cumulus being one of those. They're working with the OPNFV group, and we've installed basically a central office-like setup back in the Bay Area using open hardware. And so we're going to show a demo on some of that work, and this is work that really got kicked off literally 2 months ago. And I threw a challenge out to our team to see, hey, let's go ahead and contact some of our solution providers and see how quickly we can take open hardware that's ideally suited for a cell site or a central office, and let's see how fast we can install that. So again, this kicked off recently this summer, and we're going to get to see a demo today. So with that, I'd like to introduce Heather Kirksey. She's the VP of Ecosystems and Community within the Linux Foundation, focused on the networking projects under that foundation. So please welcome Heather.
Hi, good morning, Amsterdam. It is great to be here at the Open Compute Summit. I actually spent last week here at the Open Networking Summit, which was a summit focused on a lot of the software open source projects that I work with. So it's great that we were able to have that continuity and be able to talk to both audiences about the collaboration that we've been doing. So What I'm going to talk to you about this morning, and we're going to end up seeing a demo around, is around the virtual central office. And it's a term I've been hearing, sort of used more and more here. But for those of you who, don't have a long background in the telecom industry, central offices are places where, phone gear and a lot of gear necessary for kind of general internet connectivity has, occurred for a long time. These days, or sort of in the past, it's been mostly, very proprietary gear, very geared towards one function, whether that's a router or a switch or a CG NAT or something else. And as the telecoms are modernizing their infrastructure more generally through the use of SDN and NFV, so moving a lot of the intelligence into software and using less purpose-built equipment and more white box equipment and things like OCP solutions, which we're very excited to see. They've been on this journey to modernize the central office. That allows them to start offering a lot more services, to have a lot more flexibility, a lot more service agility, and really just sort of a lot more software-oriented modernization. So, where we are, where we have been are sort of that plethora of networking gear out there. And where we've started to get to today is really beginning to start putting in, sort of moving away from that bespoke hardware, moving to things like OCP solutions in the CO, beginning to use open source software to provide a basic platform for a lot more applications out there. We've started disaggregating in a lot of places, so stuff is a lot less monolithic. And sort of where we are is kind of in the journey around the middle box. And then looking ahead, we'd like to see a lot more open source hardware out there. We'd like to continue to look at things like cloud native and deploying, sort of moving from VMs to even containerized applications out on the CO, and then going from the CO even further and further into the edge. I was just hearing Bill talk about sort of some edge groups going on, looking at edge optimized hardware. We have a lot of work going on in Linux Foundation projects looking at sort of what the software requirements are. So I think it's great that we continue this collaboration together. So there are a lot of use cases that can be addressed by the reimagining the central office. Last summer, we collaborated with OCP and a number of organizations on a first version of a virtual central office, and there we shared residential use cases. So we onboarded what's called a BNG in telecom world. If you've ever spent any time with telecom people, you will know that we cannot resist an acronym. So BNG basically sort of provides subscriber-oriented services for residential. So we showed that we could get that onto OpenStack software using Open Daylight as an open source SDN controller and onto some OCP servers. We also showed some enterprise virtual customer premises equipment use cases. So when we thought about doing this year, we wanted to show mobile, and 5G is a important thing these days. When you talk about the VCO, Virtual Central Office, for residential and enterprise, you get a lot more flexibility, a lot more agility. We did some business modeling with Intel and saw that you could get around 30% CapEx, OpEx reduction. The difference between that and sort of looking ahead to the 5G mobile network is really a lot of the 5G use cases really demand this. So it's a baseline necessity to be able to go into the central office and even further onto customer sites, cell towers, cell sites. And so it's an area of a lot of focus across a lot of projects going on these days. And that's sort of where we're going to spend some time today. So, kind of over the past several years of our NFV and SDN journey, open source hardware journey, we've gotten a lot of experience, sort of in our central data centers, in our central clouds, beginning to move that way. So, now we're going to that network edge where, you've got central offices, towers, where you've got your LTE connectivity looking ahead to 5G connectivity. Then going out to the customer premises. And then what that enables is a lot more high bandwidth, low latency applications. The requirements from 3GPP for 5G are very stringent that way, so that you can get really cool AR, VR things, autonomous vehicle connectivity, drones. So if I were Oprah, I would say look under your seats. You've got some AR, VR goggles, and that's the demo that we're going to show. Don't have that level of resources. So what we're going to be showing shortly is going to be more of a phone call. We're going to talk a little bit more in detail, but sort of what I want you to kind of take away from this is open source software, open source hardware. We've done a lot of work to sort of the underlying platform is going to be a 5G-enabled mobile core, as well as virtualized radio access. So these are a lot of the steps necessary for us to deploy 5G out there, and so I'm really excited that we'll be able to show some of that today. So I've talked about some of the requirements sort of as I've been talking, but really the massive scale, if you think about all these edge sites, being able to manage those, being able to virtualize things like the RAN, being able to put your different types of network splits into software so they can occur at different places based on the sort of use case that you're trying to do, building things on top of sort of well-known components out there like OpenStack and Kubernetes, being able to do assurance and end-to-end orchestration. So sort of taking those telecom requirements, we've put together a demo. This is our general software stack. You can see that we've got the OCP for servers, hardware, white box switches, and then we build on top of, for this, OpenStack, SDN, a controller for Open Daylight to program the switches, also do some of the SDN control work. And then we have got a number of element management and applications on top of that. Just point out Open Air Interface is a new open source project we work with. They're providing a lot of the virtualized radio access components and the sort of the next gen mobile core. So with that being the software stack, I would like to invite on stage Rajiv Sharma to talk about the hardware aspect of this entire demo that we've built. Rajiv, please come join me.
Thanks, Heather. Hi, folks. Thank you. So Linux Foundation is working on the software stack for the past 2 years, and today I'm going to talk about the hardware. As you guys see on the slide, on July 20th, Mytek, they boxed up all the equipment that was necessary for the VCO demo. And a few weeks later, they pretty much put all that equipment onto the truck. And a month after the initial conversation started with Mytek, we had that hardware installed onto the Amsterdam data center. After that, 10 days after the hardware was here, Red Hat team remotely installed the software and made sure that everything is all OK. And 30 days later, right now here, we have everything is all set up for the VCO demo. The key takeaway from this slide is if we go back 30 days earlier, when the Red Hat team was trying to install the software, debug, and triage it, by the way, we had the hardware right there a week ago for the ONS Summit. So literally, we didn't even need 4 weeks. We only needed 3 weeks. Back to Heather.
So just really quickly, this is the topology of the lab back in San Jose. So what we're emulating here is a central office in San Jose and a branch up here on stage. So back in the Cumulus lab, we have a number of compute and storage nodes, a full leaf and spine switch fabric, and some handsets in a Faraday cage connected to software-defined antenna. Tilla's going to talk a little bit more about this when I bring him up for the demo. But the thing is, this is what's back in San Jose, and it's connecting to this branch here with the hardware from Circle B and Mytek. And so just want to make sure that we understood how everything was connected, and you can sort of keep talking about what we've got here on stage.
All right, so we took a very simplistic approach to virtualize our central office. So let's take a quick snapshot of the hardware that we have it right there for the VCO demonstration. as you guys see on the slide here, we have 4 Open Rack compute sleds using a shared power, and it is connected to the open source switch. And I'm going to talk more about these Open Rack compute sleds in my next slide. As you guys see here, these sleds have been housed in an enclosure, right? And I will also talk about the enclosure in my following slides. So first of all, thanks to MyTech for providing us the sleds. Really appreciate about it. And these are very standard sleds that you can find in a typical traditional data center. And you guys see the configuration of all those sleds right there. Moving on, let's talk about the enclosure, as I said. And this is very unique. And again, thanks to MyTech for providing us the ESA chassis. And one thing we really recognize it, because we believe that this is a very ideal use case for the telecom customers, where they have a hard requirement to have a legacy 19 inches rack. And you guys see here all the things and the piece parts that this ESA chassis has it. And by the way, thanks to Circle B for providing us the open source switch.
And no, that sound is not part of the demo. I'm not sure what that is. Yeah. Oh, OK. All right, we're validating that we're fine. OK, cool. Thank you for the data. All right. We're doing a live code demo with a live call back to the US on stage during Keynote. So, of course, we'll also have some alarms going off. So thank you, Rajiv, for talking about the hardware we've got here. One important thing to note, he mentioned the importance of legacy in telecom. We still have to, we're putting these things in COs, in cabinets, in cell towers. So, we don't get to start fresh with brand new greenfield data centers. So with that, I would like to invite Attila on stage. Can y'all still hear us, or do we need to?
Well, it should be over in a minute or so.
Yeah, I was going to say, we'll just keep going, because why not? All right, so Attila de Groot is a senior systems engineer at Cumulus, and Cumulus has been hosting our VCO for us over in San Jose. He's going to talk a little bit about the demo topology for us.
So in our topology, in the spine leaf topology that you saw earlier, what we have connected is the virtual central office. But the important thing is that we have a Faraday cage, and there are 2 phones in there. And what you'll see in the demo later is that we can remote control them both. And I see that we already switched the slide. But let me just go into the demo right now then. So you see the 2 phones here, and the left one actually is not connected. I have switched on airplane mode. And what I'll do is I'll turn that on, and in a bit you should see the 4G connection. As Heather already explained, we didn't have the 5G handsets, but the environment is made for 5G already. So what I'd first like to see or show you that it's actually live. And there's a bit of delay because this is coming from the US. But so I can show some new tweets, and also from the hashtag that we're using for OCP here in Amsterdam. And that should all just work. So we should see the latest tweets here. Now, what are we going to do? So these 2 phones are next to each other. And the left one is actually going to play some music on its speaker. And we have chosen Heather's favorite song, apparently. So we're going to play that, and on the phone that's next to it, I'm going to call Heather here, and that is going over the VPN connection, over LTE to this branch office. And Heather should be receiving a call in a bit.
Why, look, I got a call right here. And it looks like there is some music playing. So we can't have anybody in the Faraday cage. So the music, the other phone playing music is how we're getting that. So here, we can plug it in. You can all hear, I think.
Or not. Yeah.
All right, so this we can turn.
Yeah.
Yeah. All right, so just to sort of clear up, these are basically emulations of screens back in San Jose, and they just called real time, no smoke, no mirrors, live code, live internet connectivity, live machines here to us on the stage. So I always love it when friends call me and play me Kenny Rogers and Dolly Parton. I now refer to this song as Islands in the Mobile Data Stream. But so if you are interested in learning more about how we've been using open source software and open source hardware to virtualize the central office, look ahead to the edge and look ahead to 5G. We have a booth here at the Linux Foundation networking. We are sort of around the corner that way as you leave the auditorium. And I am doing a session in the engineering workshops in the telecom track tomorrow. So I look forward to seeing you all there if you want more information. All right, and then Rajiv, come on back out because I want to give some great thanks. These are the ecosystem partners who were involved in our project. So we had a number of companies who were bringing together their open source distributions, their proprietary products to help make this work, as well as their hardware. Special thanks to Cumulus for hosting our lab, and special thanks to MyTech and Circle B for getting our branch office together so quickly. And finally, as I mentioned, it was great hearing John's talk about open source this morning. This was a collaboration amongst 5 different open source consortia as well, all of who produce various parts of the stack. OPNFE focuses on integrating this together and sort of bringing it together for telecom use cases. And this was just a really amazing experience. And also, it takes guts to do live code demos on stage. So just thanks again to these guys for all of their work building this up and being brave enough to come on stage and do it. So let's give them a round of applause.
Thank you.
All right. All right, cool. And I think Bill? Yeah. Yep.
Hey, thanks a lot. Yeah, thank you to our ecosystem partners. Thanks for the Linux Foundation and Attila and Rajiv for the demo. We mentioned the summit, World Global Summit in 2019. I'd like to do a quick video and introduce you to that summit and invite you to attend.
Please welcome Steve Helvey, VP of Channels.
Good morning, everyone. Thank you very much. Hopefully that video gives you just a little sense of what takes place in California every spring. So I encourage you, if you are traveling in that region during that time of year, it's probably worth your time to check it out. So it's an amazing event. And special thanks to Rajiv and Heather and Attila for that very alarming presentation. All right. Okay, just a couple wrap-up items before lunch. Thanks again to all the sponsors. Couldn't do it without you. Really, really appreciate all your support. And for those of you throughout the day, even after all of these great presentations and speakers, if you haven't found happiness, we've dedicated 1 hour toward the end of the day for you to enjoy a nice happy hour. That's in the Expo Hall right outside here. The Expo Hall is open today until 6 and tomorrow until 3 p.m. And if you haven't had a chance to look at some of the displays, there's a lot of OCP gear out there, so I really encourage you to take a look at all the great solutions. This is a pretty exciting announcement. The formal announcement came out 2 days ago where we have 3 members, Switch, Data Centers, Circle B, and Rittel, have all come together to create an OCP Experience Center, where they've actually taken OCP hardware and deployed it within Switch data centers for the purpose of testing, POCs, and demoing. They are giving a tour tomorrow to this facility at 4 o'clock. If you're interested, email ocp@circleb.eu, and he'll put you on the list. If you can't make tomorrow's tour, go ahead and email them anyway. They'll make time for you at a later date, and they can also share with you some of their plans for expanding this Experience Center. We're expecting big things. In fact, the VCO demo after this event goes back to Switch Data Centers, where you can take a look at it in more detail. As Bill mentioned earlier, as you're walking around, taking a look at all of the solutions, don't hesitate to jump on the marketplace, which is based off of our website. Gives you a comprehensive list of all of the OCP solutions that have been through the branding and the recognition program. And lastly, to make your next 2 days a little bit easier to schedule, we have a tool. The code and the link will be broadcast throughout the monitors throughout the exhibition hall. Have a great summit. That's it. Lunch.